Alright, so what we want to do now is we want to look at, we want to review partial differentiation. Before we start reviewing partial differentiation, let me, in fact, go over just normal differentiation, ordinary differentiation, or what's differentiation of, which is differentiation of a function of a single variable, right? So they're all the same thing, right? So ordinary differentiation and just differentiation of a single variable here, and here the single variable is x. It refers to the same thing. Okay, so how you normally differentiate and how you know how to differentiate is just by using certain rules, right? So for example, over here, f of x is equal to x squared. To differentiate this, you know we're going to use a power rule, right? So when you differentiate the x squared, the 2 comes down in front, and then you get x2 minus 1, right? So you get 2 over here and x to the power 1, so you get 2x over here, right? Okay, so what you do in there when you're differentiating is you're using a certain rule, which is power rule, right? Then you have other rules as well that you can use, say like product rule, quotient rule, and so on, right? One thing you want to note is that, and you probably learned this when you were doing derivatives for the first time, is that you can calculate the derivative of a function at a specific point, specific value a over here by using this limit formula, right? Okay, so this is the original function. You evaluate your function at the point that you're interested in, which is a. Then you have f of a plus h, right? So h is, if you want, like a step parameter here, and f of a plus h minus f of a on h, right? And you take the limit of this as h goes to 0, right? So you should have seen this before, right? Okay, so this here is your limit definition of the derivative. Okay, why I mentioned this is that eventually, when we're looking at partial derivatives, how you define partial derivatives for the first time is using a limit definition, right? So use this limit definition for partial derivative with respect to x. And partial derivative with respect to y also has a limit definition. So we will get back to these here, right? So this is why I am recapping this limit definition of derivative, right? Okay, so the next thing that I want you to recall about a derivative is if I have a derivative and I evaluate it at a specific value, right, a specific x value, then what I get is I get a number, and that number is equal to the slope of a tangent to the graph of my original function f of x, right, at the point that I'm looking at, right? So x is equal to a, right? Okay, so to see an example of this, let's look at your f of x is equal to x squared, right? When you differentiate with respect to x, right, you get 2x, right? And now what we want to do is we want to see what's going on when x is equal to 1, right? Okay, so when x is equal to 1, right, okay, so if x is equal to 1, right, the point on your graph corresponding to x is equal to 1 is, so the x is equal to 1, and the f of 1 is equal to 1 squared, which is 1, right? So this is the x value here. And this is your x value here. X is equal to 1, right? And then the y value here is f of 1 squared, which is, sorry, it's f of 1, which is 1 squared, which is equal to 1, right? So the point on the graph for x is equal to 1 is the point 1, 1, right? Right. Okay, so once I have this point in the graph, what I'm going to do is I'm going to consider the tangent to that point, right? Okay, so the tangent to that point, I drew it in this diagram here. The point is 1, 1, and the tangent, this dashed line over here is the tangent. Okay, so your dashed line over here is the tangent, right? And if I take my derivative and evaluate it at the point that I'm looking at, which is x is equal to 1, right? I get a value 2, right? And this value 2 is equal to the slope of this tangent over here, right? This dashed line, right? So that is the interpretation of derivative, right? If I have a function, which in this case is x squared, I look at my derivative, which again is a function, but now I evaluate that function at a specific point, which is x is equal to 1, right? At that x is equal to 1, that corresponds to a point in the graph. And if you look at the tangent, right, if you look at the tangent to this point on the graph here, the slope of that tangent is equal to the derivative evaluated at x is equal to 1, right? So f prime 1 is equal to 2, and that's the slope of this tangent here, right? Okay, so this over here is a graphic just showing basically it's the same thing, right? Okay, so your function over here is x squared, same function that I was talking about, right? Your derivative f prime of x is equal to 2x, right? And what we're looking at is when x is equal to 1, right? So here when x is equal to 1, you have a point on the graph, right? Okay, and the tangent is this green line over here, and the slope of this tangent is equal to 2, right? And this graphic over here, right, what you have is this is the original function, and this function over here is in fact a derivative function, right? Okay, so this derivative function is 2x, right? So you see in when x is equal to 1, derivative function at this is a derivative function evaluated at x is equal to 1 has value 2, right? So this value 2 is in fact the slope of this tangent over here at this point, right? Okay, so this is when x is equal to 1. This graphic is somewhat good. What you can do is you could actually change the location at this point. So let's, for example, come down to over here, right? Okay, so this is when x is equal to 0, right? And when x is equal to 0, right, the point on your graph is 0, 0, right? The tangent to the graph at that point is horizontal, right? And you expect the slope of the tangent over here, because this tangent line is horizontal, you expect that slope to be 0, right? And that agrees with what the f prime is, right? If I put x is equal to 0 into this, I'm going to get 2 times 0, which is 0. Okay. All right. Okay, so now let's consider, say, partial derivatives, right? So recall this is the definition of an ordinary derivative, right? Notice what you're doing is you have, if you want the ordinary derivative at a specific point, specific value a, right? What you're going to do is you're going to take a and you're going to add h to it, right? Okay, and you take f of a plus h minus f of a, right, on h here, right? All right, so similarly, if I want to define your partial derivative, now this is now a function of two variables, right? Okay, so if you have a function of two variables, you can differentiate with respect to either variable. You could differentiate with respect to x, right? Or you could differentiate with respect to y, right? When you differentiate with respect to x, what you're getting is the partial derivative of f with respect to x, right? Okay. If you differentiate with respect to y, right, then what you get is you get partial derivative of f with respect to y, right? So in this case, for this function, you have two variables, right? Okay, and because you have two variables, you can differentiate with respect to either function. Okay, so if I want to evaluate partial derivative at some specific value for x and y, right? So by big X over here, I mean, sorry, by this dark X over here, right? I mean a point, arbitrary point xy, and if I want to get the partial derivative at point when this x over here is equal to a and this y over here is equal to b, right? How you define it, right, is by a limit, right? And what you want to do is you want to compare this limit definition to this limit definition. And what you want to realize, it's very similar, right? Matter of fact, if you didn't have this b over here and you didn't have this b over there, it would be the same thing, right? Okay, so one way you can read this limit definition is what you're doing now is here, what you're doing is you're changing the x values over here according to h, right? You're keeping the y value fixed, right? The b is not changing, but the x value is changing according to this h here, right? And what you want to do is you want to see you want to get an idea rate of change when you just change in the x values here, right? Okay. Right, so this partial derivative here is denoted as f of small x, right? Or del f del x, right? Sometimes I would just in class or I would just say df dx, right? But strictly speaking, this is del, right? So this is del f del x, right? Okay, so your partial derivative over here, which is you can evaluate via, which is defined via this limit, is denoted this way or this way, right? And typically we will use this notation here, right? The del f del x over here, ab. Right. Okay, now likewise we could define how we define partial derivative at a specific point AB, right, is again via limit definition, right? And again, if you're looking at this over here, right, okay, so if you look at this definition over here, this definition here is very similar to a definition for ordinary derivative, right? And matter of fact, it's very similar. Definition for partial derivative for y is very similar to a definition for a partial derivative with respect to x, right? The point here is that here what you were doing is you're changing the x values, right? And you're keeping the y constant, right? So this is for the partial derivative with respect to x, which we just saw. You're changing the x, but you're keeping the y constant. This is b here, and this is b here, right? When you're differentiating now with respect to x, right, what you're doing is you're keeping the x constant, right? So here, this is a over here, this is a over here. And what you're doing now is you're changing the y values, right? So this is b plus h and b over here, right? All right. Right, so that's how you define your partial derivatives. You define them via limits, right? But I mean, practically, you're not really going to use these when you're doing your calculations, right? Where you do use these is when you're actually creating, say, like rules and so on, right? So, for example, what I mean by creating rules is, well, if you think about it, where does, say, product rule come from, right? I mean, you know what product rule is, right? If you want to differentiate a product here, differentiate the first term and you leave the second term alone. And then you add what you get by leaving the first term alone and then differentiating the second term, right? Okay, so that would be what product rule is. Where product rule comes from is it comes from this limit definition, right? That is where it actually came from, right? So likewise, the use of this limit definition is to actually prove rules, right? But it's not that useful when you're doing actual calculations, right? Okay, so how do you actually find the partial derivatives, right? So if I have a function of two variables and I want to get the partial with respect to x, right? The idea is what you do is you just treat the y as if it was like a constant, literally a constant, and you just use your normal rules from before, and you differentiate with respect to x, right? Okay, so let's look at an example of that, right? I have this function f of xy is equal to x squared y cubed, right? And I want to get my partial with respect to x, first of all, right? So in this function over here, what you're going to do is because you differentiate with respect to x, you're going to treat y as a constant, right? So you could, if you never really did this before and you want to get probably familiar with it, you could literally just say, well, okay, I'm going to put in a constant here for y, right? So let's say we put in 11, right? Some constant. Now my function over here is x squared times 11 cubed, right? Okay, this is not what it really is. What it really is x squared y cubed, right? But what I'm doing here is I'm just literally treating the y as a constant, right? Now, if I was going to differentiate this, well, how would I differentiate this, right? Just normal, using normal differentiation for the x, right? Well, this is you differentiate the x squared, and then the constant is just going to come along, right? So you'll get a 2x over here, and then the constant will then just come along, right? Okay, and now that tells you how you're going to get your answer over here, right? Remember the 11 was just equal to y, right? So what you could do is you could put back the y over here, and then your answer would be 2xy cubed, right? Okay. All right, so that is what I mean by treating the y as a constant, but when you doing these problems, and so you're not really going to put in like a 11 or so for the y, right? What you're going to do is you're going to look at this, right, when you're differentiating. And if you're differentiating with respect to x, you want to realize, well, now the y cubed is just a constant, right? And if you differentiate in respect to x, and this y cubed is now just a constant, all you're doing is you're differentiating the x squared, and the constant will just come along for the ride, right? Okay, so you differentiate the x squared, you're going to get the 2x, and then the constant y cubed just comes along for the ride, and you get your answer, right? Okay, right, so let's do a next one, right? I have the same function over here, x squared y cubed, right? And now I want to differentiate with respect to y, right? Okay, so the rule is that if I want to differentiate with respect to y, now you're going to treat x as a constant, right? Okay, so here I'm going to differentiate with respect to y, right? And I'm not going to substitute values. If you want, you could read this and see, but we just do it over here. And now we treat, if we differentiate in with respect to y, the x is now a constant for us, right? Okay, so this x squared term is a constant for us. And now when we differentiate in with respect to y, we just treat in y as if it's just a variable just like x, right? You differentiate the y cubed, you're going to get 3y squared, right? Okay, so you'll get your 3y squared. And then this x squared, because it's just behaving like a constant, will just come along as a constant in your answer. So you get 3x squared y squared. All right. Okay, so let's do a next example here, right, of the partial differentiation. Right, okay, so we're looking at this example. Now the function of two variables f of x, y is different from what we had before. It's x squared times cos x plus y, right? All right, I'm going to get partial with respect to x and partial with respect to y, right? Okay, so first let's do the partial with respect to x, right? So if you're doing the partial with respect to x, right? Right, so you look at this here and you realize, well, I have x squared times cosine x plus y, right? And going back to the silly stuff that we did, that where we put in actual constant for y, right? And we get, say, something like this. If you see something like this, you probably know how to differentiate this just using ordinary differentiation, right? Using ordinary differentiation, you need to use product rule here, right? You need to differentiate the x squared, bring along the cos x, and then leave the x squared and then differentiate the cos x cos to get minus sine, right? Right, and that's exactly what we want to do over here when we're doing the partial differentiation, right? We need to differentiate this using our product rule, right? You differentiate the x squared first, right? And then you get your 2x over here, right? Times the cosine xy. And then you bring along the x squared. So this is part of the product rule here. And now what you do is this cos x plus y, you're going to differentiate this with respect to x, right? Now if you differentiate in the cosine x plus y with respect to x, right, the cosine will become minus sine. And then you need to differentiate the inside. Okay, you're gonna differentiate the cosine, right? You're gonna get minus sine x plus y, right? And then you multiply by the derivative of this x plus y with respect to x, right? And if I differentiate this inside here, x plus y with respect to x, I'm just gonna get 1, right? So really differentiating the cos x plus y gives me minus sine x plus y, right? Which is this here. So I get minus sine x plus y times x squared, right? Okay, so in this particular case, I needed to use product rule, right? Right. Okay, so now let's differentiate with respect to y, right? Now, if I'm differentiating this with respect to y, right? Again, I can look at this as a product, sort of, right? X squared times cosine x plus y. But now that I'm differentiating with respect to y, right? This x squared is really is a constant, right? As far as y is concerned, right? So it's a constant. So it's as if you're just differentiating a constant times cosine, right? And if you differentiate in a constant times cosine, all you need to do is just differentiate the cosine, right? So in this case, if I'm differentiating with respect to y, there's no need for a product rule here, right? All you need to do is just differentiate this over here because this is what has the y, right? You don't need to differentiate this because this does not contain any y. And because it doesn't contain any y, it's really just a constant as far as y is concerned, right? So, and because it's a constant, you could actually, when you differentiate it, you could literally pull it out. So I'm differentiating x squared cos x plus y. I could pull the x squared out, and all I need to do now is differentiate the cosine x plus y, right? And differentiating the cosine x plus y now with respect to y, it's very similar to what I had before, right? Differentiate the cosine x plus y to get minus sine x plus y. But strictly speaking, I would need to multiply by the derivative of the inside, right? And the derivative of the inside is just going to be 1, and I get minus x squared sine x plus y. Alright, let me make one point about what I said for differentiating. For example, over here, differentiating cosine x plus y with respect to y, right? Okay, so what I said is what you do over here is you differentiate the cosine x plus y to get minus sine x plus y. But then what you need to do is you need to differentiate the inside and multiply, right? And when you differentiate the inside and multiply, you actually get 1, right? Okay, so what do I mean by that, right? What I mean by that is, for example, this over here, right? So what you're doing is using chain rule, right? Right, so if you want to differentiate cos squared, right? If you want to differentiate cos of x squared, right? You differentiate the cosine to get minus sine, so you get minus sine x squared. But you need to differentiate the inside over here and multiply by it, right? That's the chain rule. Okay, and when you differentiate the inside, which is x squared, you get 2x. So your answer over here is minus 2x sine x squared, right? So this is just a extraneous example that I cooked up to illustrate the point, right? Okay, so going back to our problem here, what we wanted to do is differentiate cos x plus y, right? Okay, so similarly, if I want to differentiate cos x plus y with respect to y, this is now partial differentiation, right? What you're doing is you're treating the x as a constant and you're differentiating with respect to y, right? So you differentiate the cosine, right? You're going to get minus sine x plus y, right? But then I need to differentiate the inside over here with respect to y and multiply by it, right? Similar to like what I did up here, right? Okay, and when I differentiate this inside over here with respect to y, I differentiate the x with respect to y gives me 0. Differentiate the y with respect to y gives me 1. So I get 0 plus 1, which is 1. And I get 1 times minus sine xy, which is sine of xy, right? Okay. Alright, okay, so let's consider second derivatives now of partial derivatives, right? So second partial derivatives. Okay, so before we get into second partial, I'll just remind you as to what a second derivative is, right? So if I have this function over here, f of x is equal to sine x, your first derivative, or just a normal derivative, is what you get by differentiating your function once, right? So you differentiate the sine x and you get cosine x, right? Your second derivative is what you get by differentiating the first derivative, right? So what second derivative means that you differentiate twice, right? So you had your first function, your function to start off with, you got your derivative, and then you differentiate that again, right? And that's your second derivative. So your first derivative is cos x. In order to get your second derivative, you need to differentiate that. So the cos x, you differentiate, and when you differentiate the cos x, you get minus sine x, right? So your second derivative in this case is minus sine x. If your original function is f of x is equal to sine x. Right, so notice how you got your second derivative here, right? You got your second derivative by taking your first derivative here and differentiating it again, right? Okay, so that is how you're going to define your second partial derivatives, right? So if I want to get the second partial with respect to x, right? And here, this means I'm going to differentiate with respect to x twice, right? What I need to do is first get the partial with respect to x, and then differentiate that again with respect to x, right? So it's the same idea as over here, right? Similarly, if I want second partial with respect to y, right? What you do is you first get your partial, you get your first partial with respect to y, and then you differentiate that with respect to y, right? Right. Now what I have here is these are mixed derivatives now, right? So what this means, how you want to read this is you want to read it going say it this way, right? From right to left, right? So you differentiate in with respect to x first and then with respect to y, right? So what this means over here is you differentiate with respect to x first, and then that result you differentiate with respect to y, right? And this one here is what this means is you differentiate with respect to y first, and then you differentiate with respect to x, right? Now it turns out for the cases that we will look at in this class, right, where we're looking at mainly functions with mainly continuous functions, right, or functions with continuous partial derivatives. What's going to happen here is that these are going to be equal, right? These are mixed partials. This is when you differentiate with respect to x first then y, and here this is when you differentiate with respect to y first then x, right? Okay, so as I mentioned that in this class, what's going to happen most of the time is, well, all the time for us, right, is that these are going to be equal to each other, right? And these being equal to each other, that's called Clairaut's theorem, right? And the condition that under which this occurs is that your second partials here are continuous, exist continuous on a region that we're talking about, right? And that will be satisfied in our cases, right? Okay. Right. Okay, so let's look at an example of calculating second partial derivatives, right? Okay, so if I remember, if I want to get second partial derivatives, right, I would need the first derivatives to start off with, right? So I'd need the df dx first, the del f del x, and the del f del y, right? Okay, so if I want to get second partial derivatives, first thing is I need to differentiate with respect to x first, right? If I differentiate with respect to x over here, the x squared here would give me the 2x, and then the y would just come along, right? And differentiating this with respect to x, here I'll get a 2xy as I just said, right? But this will give me 0, right? So I get 2xy, right? And if I differentiate this with respect to y, right, the y will become 1, and then the coefficient of over here, the constant, will come along, which is x squared, right? And then I differentiate the y cubed to get 3y squared, right? Right, and to get your second partial with respect to x, right, so you differentiate with respect to x twice. You just take this here, and then you differentiate it once again with respect to x, right? So you take it 2xy, differentiate it with respect to x, and you're going to get 2y, right? So this is the second partial with respect to x. To get the second partial with respect to y, you're going to take this over here and differentiate it with respect to y. When I differentiate this with respect to y, I'm going to get 0 here. And I differentiate this with respect to y, I'm going to get 6y, which is this. Right. Okay, so now let's do a mixed partial, right? So this means that I differentiate with respect to y first and then with respect to x, right? So when I differentiated with respect to y first, I got this over here, which is x squared plus 3y squared. And now I want to differentiate it with respect to x, right? When I would differentiate this with respect to x, I'm going to get this will become 0 here, but I differentiate the x squared to get 2x, which is this. Now, the second partial with respect to x first, then y, right, means that I need to work this out first, which is the the 2xy, and then differentiate this with respect to y. When I differentiate this with respect to y, the y becomes 1, and the 2x comes along and I get 2x, right? Okay, and you want to notice this is an example of what I was talking about. These, even though you differentiated this with respect to y and then with respect to x, and here x and then y, you ended up getting the same answer, which is 2x, right? Okay, and as I said, it only holds, well, it holds in some general sort of situations, and those general situations would include the cases that we would have in this class, right? You sort of have to come up with, kind of cook up a more sort of sophisticated example to get these to not be equal to each other, right? Right. Okay, so what we talked about was functions of two variables, right? Now you could also take partial derivatives for functions of three variables. It's the same idea, right? Okay, so here I have a function of three variables, x, y, and z, right? Notice on this expression here, I have x over here, y here, and z here. In this term, I have x and z terms in it, right? It doesn't have any y, but doesn't stop it from being a function of three variables. And now what I want to do is I want to differentiate with respect to x, right? So if you differentiate with respect to x here, it's the x that you're differentiating and everything else is a constant, right? So when you're differentiating this here, the yz would be a constant, and then you differentiate the x squared to get the 2x. So you get 2x yz. And if I differentiate this over here with respect to x, again you differentiate the x to be 1, right? And then this just comes along, right, as a constant, and so you get 1 times e to the z, which is e to the z, right? Okay, so that's the basic idea of how we do it. And getting the mixed partials is the same idea, right? So for example, if I want to get let's say I want to do this one here, right? So what this means is I differentiate with respect to x first, then with respect to y, right? Okay, now the derivative with respect to x is this over here already, right? And now what I want to do is to get this partial, second partial, where I differentiate with respect to x first then y. What I need to do is differentiate this with respect to y. When I differentiate this with respect to y, this goes to 0 because it doesn't have any y in it. And this over here, the y goes to 1, but the constant, which is 2xz, comes along. So I get this, right? So it's the same idea as evaluating partial derivatives for a function of two variables, right? Okay. Right, so you'll do some more of these in your tutorial, right, and so on.